A buffer is a special solution that resists significant changes in pH when small amounts of an acid or base are added. In acid-base titration, buffers play a key role in maintaining a stable pH, particularly near the equivalence point. Let's break it down. 1. Components of a buffer solution. A buffer is typically made of either a weak acid and its conjugate base, or a weak base and its conjugate acid. For example, consider a buffer containing ethanoic acid, also called acetic acid, CH3COOH, and acetate ions, CH3COO. Ethanoic acid partially ionizes in water, establishing an equilibrium, CH3COOH plus CH3COO. 2. Adding sodium ethanoate, CH3COO. When sodium ethanoate dissolves in water, it provides more CH3COO ions. The combination of CH3COOH and CH3COO creates the buffer. Explanation of the formulas in buffer solution calculations. 1. Ion concentration in weak acids or bases. The first formula relates to the concentration of hydrogen ions, denoted as H+, and hydroxide ions, denoted as OH-, in solutions of weak acids or bases. For weak acids, the formula to calculate hydrogen ion concentration is H+ concentration equals the square root of the product of the water ionization constant, denoted as Kw, and the base dissociation constant of the conjugate base, denoted as Kb, multiplied by the initial concentration of the weak acid, denoted as C0. In words, Kw is the ionization constant of water, with a value of 1 × 10⁻⁻14 at 25 degrees Celsius. Kb is the base dissociation constant of the conjugate base of the weak acid. C0 represents the initial concentration of the weak acid. 2. pH and pO calculations using the Henderson-Hasselbalch equation. The second set of formulas is used for buffer solutions, based on the Henderson-Hasselbalch equation. For acids, pH calculation. The formula is pH equals the negative logarithm of the acid dissociation constant, denoted as pKa, plus the logarithm of the ratio of the conjugate base concentration to the weak acid concentration. In detail, pKa is calculated as the negative logarithm of Ka. The conjugate base concentration, represented as a minus, refers to ions like acetate or CH3COO-. The weak acid concentration, represented as Ha, refers to acids like ethanoic acid or CH3COOH. This formula is used to calculate the pH of a buffer solution by considering the ratio of the conjugate base to the weak acid. For bases, pO calculation. The formula is pO equals the negative logarithm of the base dissociation constant, denoted as pKb, plus the logarithm of the ratio of the conjugate acid concentration to the weak base concentration. In detail, pKb is calculated as the negative logarithm of Kb. The conjugate acid concentration, represented as BH+, refers to ions like ammonium. The weak base concentration, represented as B, refers to substances like ammonia. This formula calculates the pO of a buffer solution containing a weak base and its conjugate acid. Hello, let's explore an interesting question about buffer solutions and pH calculations. Here's the scenario. We have a buffer solution prepared by mixing 0.2 moles of acetic acid, which is Ha, and 0.1 moles of sodium acetate, which is a minus, in 1 liter of water. The acid dissociation constant Ka of acetic acid is 1.8 × 10⁻⁻5. Now we need to solve the following. Part A. Calculate the pH of the buffer solution. Part B. If 0.01 moles of hydrochloric acid, or HCl, is added to the solution, calculate the new pH. Part C. If 0.01 moles of sodium hydroxide, or NaOH, is added instead of HCl, calculate the new pH. First, we calculate pKa using the formula pKa equals negative log of Ka. Substituting the given value of Ka, pKa equals negative log of 1.8 × 10⁻⁻5. This gives us pKa equals 4.74. Next, we substitute the concentrations into the Henderson-Hasselbalch equation. The concentration of a minus is 0.1 molar, and the concentration of Ha is 0.2 molar. So, pH equals 4.74 plus the log of 0.1 divided by 0.2. Simplifying, pH equals 4.74 plus the log of 0.5. The log of 0.5 is negative 0.301. Therefore, pH equals 4.74 minus 0.301, which equals 4.44. So, the initial pH of the buffer solution is 4.44. Step 2. Calculate the new pH after adding 0.01 moles of HCl. When HCl, a strong acid, is added, it reacts with the conjugate base A- to form more HA. The formula for the reaction is A- plus H plus gives HA. The moles of A- decrease by 0.01, and the moles of HA increase by 0.01. After the reaction, moles of A- equal 0.1 minus 0.01, which is 0.09. Moles of HA equal 0.2 plus 0.01, which is 0.21. Since the volume of the solution remains 1 liter, the concentrations are: the concentration of A- is 0.09 molar. The concentration of HA is 0.21 molar. Substitute these values into the Henderson-Hasselbalch equation. pH equals 4.74 plus the log of 0.09 divided by 0.21. Simplify the ratio to 0.428. The log of 0.428 is negative 0.369. So, pH equals 4.74 minus 0.369, which equals 4.37. The new pH after adding HCl is 4.37. Step 3. Calculate the new pH after adding 0.01 moles of NaOH. When NaOH, a strong base, is added, it reacts with the weak acid, HA, to form more A-. The formula for the reaction is HA plus OH minus gives A- plus water. The moles of HA decrease by 0.01, and the moles of A- increase by 0.01. After the reaction, moles of HA equal 0.2 minus 0.01, which is 0.19. Moles of A- equal 0.1 plus 0.01, which is 0.11. Since the volume of the solution remains 1 liter, the concentrations are: the concentration of HA is 0.19 molar. The concentration of A- is 0.11 molar. Substitute these values into the Henderson-Hasselbalch equation. pH equals 4.74 plus the log of 0.11 divided by 0.19. Simplify the ratio to 0.579. The log of 0.579 is negative 0.238. So, pH equals 4.74 minus 0.238, which equals 4.50. The new pH after adding NaOH is 4.50. Summary: the initial pH of the buffer solution is 4.44. After adding HCl, the pH decreases to 4.37. After adding NaOH, the pH increases to 4.50. Thank you for listening.